I'm going to briefly explain how to use an interactive simulation that models evaporative crystallization with a recycle stream. And the main objective of this interactive simulation is really to show how to do mass balances, and we've picked the crystallization process to do that. So the idea is we have a fresh feed that has 15% potassium chloride and the remainder is water. It's mixed with recycle and then fed to an evaporator where water is removed. And then the stream is cooled down in a crystallizer and filter so that we remove potassium chloride crystals. But entrained with those crystals is some of the solution, so we're removing some liquid that has potassium chloride dissolved in it. But most of that solution is recycled and fed again, mixed with the fresh feed. So the flow rate of the feed can be adjusted with a slider. Temperature of the evaporator can be adjusted. That of course affects solubility, as well as the temperature of the crystallizer affects solubility. The solubility of potassium chloride is linear with temperature. As you raise the temperature, the solubility increases. So we've put a constraint on this simulation that 95% of the feed of potassium chloride, in this case we're feeding 60 kilograms of potassium chloride per hour, 95% is removed as potassium chloride crystals. And that constant, independent of the various values we picked, that may not be realistic, but we've done that just to demonstrate the mass balances. Let's look at the simulation to see how it behaves as we change parameters. Well, here's the simulation, and if we increase the feed flow rate, of course, then we have more recycle, we have more crystals that are leaving the system. If we increase the evaporator temperature, because of the constraints, we increase the concentration, and we're increasing the recycle. And if we lower the crystallizer and filter temperature, then you can see we lower the solubility, what appears here and here. So let's look at that again. If we lower the temperature, lower the solubility, and we also lower this recycle flow rate. So the important thing is that we're looking at mass balances, and we've put constraints that we're recovering 95% of the potassium chloride that enters the system.